On the other hand, there are a couple of nice things that you might get from having taken calculus in high school. In particular, in this sort of class, we're going to be a little bit shady on some of the computation stuff, in the sense that, like, yeah, I'll tell you how to do it, but we're not going to spend a lot of time practicing it, investing in it, doing anything like that, right? So you can imagine I'm going to give you the tools. There'll be a token example, but for the most part, we're going to skip it. So if you've seen that sort of stuff in high school, phenomenal, you have it. If you haven't seen that sort of stuff in high school, then it really doesn't matter, because I'm probably not going to lean on it. What it does mean, though, is that if you ever want to go take like a class that actually does lean on the computational stuff, you might have to go and learn that stuff on your own. I have this like great story from grad school where one of my friends, who's actually a teaching prof now downtown at St. George, he was teaching, I think, 136, right? And so he had a German upbringing, right? He was German, and he, and the German education system is very strong. So he basically, he took this course when he was an undergrad, and he came here, and now we're in grad school, and he's teaching, or he's TAing Math 136, and he has no idea how to compute any integrals, because that is just not a thing that you do, right? For example, it's not a thing that we're really going to do either. And so he comes and he has to like learn how to compute these integrals so he can teach us students how to compute integrals, because he has no idea, right? And so it's the same sort of thing here. In theory, we might quickly gloss over some of the computational techniques, but I'm not going to lean into them heavily, which means you're not going to know them heavily. So if you go and you take, I don't know, some stats course or something where they actually need you to compute that stuff, well, you might need to, crack open Stewart or something and take a gander, or my book, I'd go through it all, but I'm not going to spend a lot of time in this class worrying about that sort of stuff. So that's, I think, the only kind of advantage you might have if you, took some high school calculus. Now, the other thing that's kind of, I'm going to say fair warning here, is I'm going to fly. Okay, so I tend to do the limit stuff quite slowly, right? Think about how long we spent on limits. We spent a long time on limits. The limits are hard, right? Limits are really tough. For the differentiation, like I said, for the most part, I'm going to fly because it's not as hard and it's not as difficult. And it's mostly just getting a bunch of examples and simple computations out of the way so that we can get to the fun stuff. So our goal, so don't be intimidated if I go very quickly. So our goal is that we want to capture an idea about the instantaneous rate of change of a function, right? So we want to talk about the instantaneous rate of change of a function. Okay, now I have, in my undergraduate, I have a fair amount of physics experience, as I may have told you before. So I actually like to use speed as an example of this, right? Sure, yeah, mechanics. There's lots of examples of stuff that you can do. The first thing I want to do is talk about like if we want to know about the instantaneous rate of change, what's the average rate of change, right? So if f is a function, I probably should say, what its domain and codomain are, but we don't care. Its average rate of change on the interval AB is, so the average change, I guess I should say average rate of change, is f of b minus f of a divided by b minus a. Okay? Yeah, physics absolutely is a good way to practice computation. Yeah, because they'll make you compute the hell out of stuff. Okay? Now, if you don't see that this is true, the analogy I like to draw is to think about a car, right? So suppose something like f, let's say, as a function of t time, describes how far you've traveled. How far you've traveled at time t. Right? Okay, so we're saying like, let's say maybe it's not a straight road or something, but you're driving along a road and, at time, let's say t is measured in hours or something. So after 1 hour, you've traveled 20 kilometers. And after, 3 hours, you've traveled 150 kilometers, right? How would you determine your average rate of change? Well, your average rate of change in that case is your average speed, right? So the average rate of change. So in this case, the average rate of change is your average speed, right? So I don't think I'm leaning too heavily on your physics knowledge for this, but what is your speed? It's how far you've traveled divided by, or your average speed is how far you traveled divided by how long it took you to travel that distance, right? So for example, what was the example I gave? I said, f of, whoa, why is my screen freaking out? Okay. So I said f of like 1 hour is 20 kilometers. Maybe let me include the units. We don't have to, but just to give you an idea. And then let's say after 3 hours, what did I say? 150 kilometers, something like that. Could have chosen nicer numbers. Maybe let me make that 160. So after 1 hour, you've traveled 20 kilometers. After 3 hours, you've traveled 160 kilometers. If I said, what was your average speed over that time? Thank you, pen. So your average speed over that time is how far you traveled, which in this case, we can eyeball, we can see that that's 140, but how would you actually compute that? All right, you would take their difference. So we traveled 140 kilometers in 2 hours. So that means that our average speed would be 70 kilometers per hour, right? So that's the idea. That was your average speed. Now, certainly over that time period, you might have been going faster than 70K an hour. You might have been going slower than 70K an hour. But the idea is that this is your average speed, right? Now, your instantaneous speed should be your speed at any moment in time, right? Like you're driving on the road, you look down, you look at your speedometer, and it says you're traveling 55 kilometers an hour. That's your instantaneous speed. That's how far you're traveling right now, right? That's your instantaneous speed. And like, how would you compute that? Because the problem is that you don't reasonably have a way of figuring out what that number is. Speed is distance divided by time. If no time has passed, you're basically taking 0 divided by 0, right? You're saying, well, no, I haven't, at this single instant in time, I haven't moved anywhere and no time has passed. So you're dividing 0 distance traveled by 0 time elapsed, and you get some sort of nonsensical thing. So the insight, when people talk about like the brilliance of Leibniz and Newton, the insight was that in order to determine that instantaneous change, what you should do is just take better and better approximations, right? So if I want to figure out my instantaneous rate of change, what I could do is say, okay, well, how far let me compute my average speed over the next hour, right? And that's an approximation to my instantaneous speed. But I could do better if I approximate over a shorter time interval. So maybe I would do 10 minutes instead, right? And I compute what my average speed is over 10 minutes. That's getting better, but I could still have wild fluctuations in there. So what about 1 minute? What about 1 second? What about a half second? What about a nanosecond? You know what I'm saying? So the idea is that by using shorter and shorter time intervals, you get better and better approximations of what the instantaneous rate of change should be, right? So the key insight, so the average speed approximates the instantaneous speed, and this approximation gets better as we use shorter and shorter intervals. Improves as we use shorter intervals, right? Okay, so then immediately, hopefully what kind of comes to mind is you say, okay, well, I can compute those numbers, no problem. But what I really want to do is I want to take a limit, right? I want to take a limit as I let that interval over which I'm approximating go to 0, right? That's sort of the idea there. So that leads us to the definition of the derivative. So let's say, suppose I am going to try and give f a function a proper name now. F maps I to R. Okay, don't worry about I. It's just the domain. I had to give it some name and I didn't want to give it all of R. Maybe it's an interval or something. Suppose F maps I to R and C is some point in I. So we say that F is differentiable at C if this thing exists. Right, and you will notice that this is the average speed or the average rate of change here, right? And I'm taking a limit as x approaches C. So basically I'm taking a limit as I'm letting that, that approximation shrink down to 0, right? So we say that f is differentiable at C if this exists. Okay, in which case this number f prime of C here is said to be the derivative of f at C. In which case f prime of C is the derivative of f at C, okay? So we're going to compute that limit. And again, you can kind of see that that limit, as I was alluding to earlier, is like this 0 over 0 thing, right? It's certainly not continuous, because if you were to just plug C in, you'd run into trouble. You'd get f of C minus f of C, that's 0 in the numerator, C minus C, 0 in the denominator, and you run into trouble, right? Nonetheless, if your function is differentiable, then there's hopefully some sort of removable discontinuity in this difference quotient on the right-hand side, and you actually get a limit, right? So even though that difference quotient won't be continuous, it hopefully has just a removable discontinuity. Once again, now, just like with continuity, differentiability is defined at a single point, right? We talk about being differentiable at 0 or differentiable at 7 or pi or something like that. And if you're differentiable at every point in your domain, we'll just say you're differentiable, right? So let's just add that in. So if f is differentiable for all C in its domain, which we called I here, we say f is differentiable. So we don't say it's differentiable at a point, we just say differentiable because we know that means at every point, right? Okay, let's grind out a quick example. So let's say show that f mapping 0 infinity to R, let's say x maps to 1 over x squared, that's a 2 squared, is differentiable at, let's say C is equal to 2, okay? So I've got this function, it's just the function 1 over x squared, and we're gonna show that it's differentiable at 2. So all I'm gonna do, now when somebody asks you to show that something is differentiable, you have to show that limit exists. And when you show that limit exists, you're going to figure out what the derivative is anyway. So those two things are kind of tied up in one another. Usually when you're showing that something is differentiable, you often end up computing what the derivative is anyway. So that's sort of a nice little thing. So let's just compute the limit. We're just going to plug everything in, right? So we're going to get f prime of 2 is the limit as x approaches 2. And I'm not even going to plug in the function yet. I'm just going to write it out, right? Just so we can kind of keep track of what everything is and what it's doing. Now let's plug our numbers in. So I get the limit as x approaches 2, 1 over x squared minus 1 over 4 divided by x minus 2. What a mess. But nonetheless, Let me write this as a single fraction and, cross multiply the numerator. It's just algebra at this point, right? This is the most computation I feel like we've done all year. So we get 4 minus x squared times 4x squared times x minus 2, right? Now the 4 minus x squared in the numerator will factor as, negative x minus 2 times x plus 2. So that we can do some cancellation there. So x2 as negative x plus 2 all over 4x squared. Now this function is actually continuous at 2, right? We've effectively removed the removable discontinuity, so I can just plug 2 into this, and now I'm going to get negative 4 divided by 4 times 4, so that's negative 1 over 4, right? So yeah, f is differentiable. At c equals 2. And in that case, even though it didn't ask us for it, we know that that is true. Okay. So, we had to do some work there, but it wasn't terrible. It was mostly just algebra, and then recognizing that we had some polynomials, we could cancel some polynomials out, and eventually arrive at something that we could evaluate. Now, the idea here is that you can imagine it's kind of a pain in the butt to compute the derivative at 2, at 3, at 7, at 9. If I take this exact same function and I ask you to compute the derivative at another point, let's say I ask you to compute f prime of 2, or f prime of 1, or f prime of 3, the steps that you take are almost identical. There are a couple of numbers that change, but generally you're going to have this difference of squares in the numerator. You're going to factor it out. It'll cancel a term in the denominator, and you'll get your answer out. So the idea here is that often it's easier just to actually compute this in general, or it's not easier, but it's just a little bit more work to compute the set of all points for your differentiable. And this gives us the notion of a derivative function. So right now, the fact that I've kind of suggestively written the definition of the derivative almost as if it were its own function is because we're now going to talk about the derivative function, right? Up until this point, the derivative is just some number, and we'll talk about what that number is. I mean, that number is the instantaneous rate of change, right? It's your speed at that instant in time. But yeah, let's talk now about the derivative function. So if f maps I to R, let's say let D be, well, D is a subset of I, be the points where f is differentiable. So it might not be all of I. We're just going to take the subset of differentiable points, the points where f is differentiable. The derivative function is the map f prime mapping D to R, which sends C to f prime of C. Okay. So again, this might be your first kind of time seeing a function defined like this. Basically, it says all the derivative function does is you give me a point at which I know my function is differentiable, and the output of this function is the derivative value, right? Now, interestingly, in the process of computing f prime for general values of C, will actually help us determine precisely where our function is differentiable and where it's not differentiable. So let me give you an example of that. So let's use the same example as above. Okay, so same sort of thing. We've got f from 0 to infinity to R, taking x to 1 over x squared. Find, I'm going to say f prime. And strictly speaking, in order to find this function, you would need to know the set on which it's differentiable. So, well, let's figure out all the points where f is differentiable. But doing that will actually give us the derivative function, right? It's one of these things, just like above, to show it's differentiable, we're going to compute the value of the derivative. Same sort of thing here. To figure out where it's differentiable, we're going to compute the derivative function. And this really isn't much more difficult. And in fact, you'll see that it's the exact same steps. What we're going to do is we're going to compute f prime of c now for like an arbitrary value of c, right? So previously we did it for this one particular value of 2, but now I kind of want to do it in general. So I'm just going to let it be a variable. And you'll see, again, I'm just going to write down the definition of a derivative here just to really emphasize it, especially if this is your first time seeing this thing. And I'm just going to plug all of this stuff in. And then again, I am going to exactly what I did before, c squared minus x squared divided by c squared x minus c. Right, just algebra it up, factor the difference of squares in the numerator, cancel an x minus c out. Okay, so what am I going to get here? I'm going to get negative x plus c divided by c squared x squared. Okay, and I can plug c into this thing now. It's definitely continuous because the denominator is not 0. So what am I going to get? I'm going to get negative 2c all over c to the 4. And c is not 0 here, right? Because my domain doesn't actually include 0. However, if my domain did include 0, this would be my first indication that my function is not differentiable at 0, right? Because I would have this 0 over 0 thing here, which is nonsense. I guess I would still have it from here anyway. But yeah, so we have that f prime of c is negative 2 over c cubed. So our function is going to be differentiable anywhere where this thing is defined, right? And if we look at the domain of my function, the domain of the function is 0 to, open 0 to infinity. Yeah, that's every single value of c in 0 to infinity is to, makes this derivative defined, right? There's no value of c that I could plug into here that is badly behaved, right? 0 is really the only point, and that's not in my interval. So f is differentiable, period. But let me maybe just say this for emphasis on 0 infinity. And now instead of using c, I'm going to use just x again. And f prime of x is negative 2 over x cubed, like that. Okay. So this is great now, and we can see that, yeah, this actually agrees with what we found before, as it should. If I plug x is equal to 2 into this derivative function, I get negative 2 over 8. That's negative 1/4, right? That's what we found in the previous example. But the great thing now is that I don't have to go through all of this limit computation again. If I want to figure out what f prime of 1 is, all I do is I plug it into this function. I would get negative 2 over 1 cubed. That's negative 2, voila, perfect, right? So now I've got this function which just outputs for me the value of the derivative at every point that it can. And I don't have to go through that limit computation all over again. I think there's a typo. It should be bracketless. No. So c minus x squared is c minus x all over c plus x. And then I canceled out this x minus c here. But that gave me an extra minus sign because they don't match. And then I just switched the x and the c. So the thing that gets left over is a negative c plus x. And right? Does that make sense? Or are you talking about somewhere else? Because it was negative, yeah, because if it was negative x plus c and I plug c into that, I would actually get 0, right? I would get 0 in that numerator, so no, but that's okay. Like I kind of went through that algebra quickly, so I'm hoping that you just kind of kept up. I just don't want to spend like a million years doing algebra because I'm very confident that you all couldn't do it if you had to. Like I'm willing to bet some of you probably are actually not that great at algebra. Like you're probably better at proofs than you are at algebra. But again, I'm confident that, modulo silly mistakes, most of you can do it. So I'm not too worried about that. Okay, so far so good. Any questions? No, we're okay. All right, so next up is the geometry of the derivative. So we have already talked about basically what the derivative represents analytically, that it's this instantaneous rate of change of the function. But it turns out if you think of a function in terms of its graph, which is very dangerous, but sometimes we're going to lean on that. If you can think about the derivative in terms of its graph, then geometrically, both the average rate of change and the instantaneous rate of change have nice interpretations there, right? So if we graph a function f, okay, so let's do that, and always try and make your graphs nice and big. It's one of the great errors that new teachers make, and frankly students, is that when you graph something, you don't make your picture big enough. All right, always, always, always draw a nice big picture. Okay, so let's say that this is the point x here, right? And we're trying to figure out what the derivative is there, and you know, or sorry, we're trying to figure out what the derivative. Let's let this be c. That's where we're trying to figure out the derivative. All right, and here's our point x. So the average rate of change is the slope of the line connecting these points on the graph. All right, so there's f of c. Let's see if I can draw f of x in here. Hopefully I got this right. Yeah, that's close enough. All right, so the average rate of speed is the slope. Oh, this is going to be tough. Let's see if I can draw this straight line. That was pretty close. I think I did an okay job there. The second rule of drawing pictures is make your dots bigger so that it looks like it went through the dots. Okay. Should we give the definition of the graph? No. You guys know what graphs are, right? I mean, if you really want, you know, the graph is usually denoted by gamma, and it's the collection of x, f of x, you know, such that x is in the domain of f, which is a subset of R2. So, I mean, like you could do that if you want, but I assume you're all kind of familiar with it and I don't want to worry too much about it. And I mean, technically, I think I gave it in the pre-handout, the pre-class handout, right, from way back in the day, right? But yeah, so the average rate of speed, so the average rate of change, right? So remember, what is that? So that's going to be f of x minus f of c divided by x minus c. Well, that's exactly the slope of this line, right? Rise over run. So we've got this length here. This is x minus c. And then f of x minus f of c is the height, is the rise, right? So the slope of this line is precisely the average rate of change. And then now you're going to have to visualize this a bit. If I was thinking, I actually would have set this up in Desmos or something so I could show you. But as I take that right endpoint, as I take x and kind of slide it along the blue curve towards the big green dot where I can, you know, at C, and I let the red line still has to go through both those dots, right? So as the red line kind of comes with it, as I slide it along that blue curve, what I end up getting is a tangent line, right? A line which just kind of nicks the curve, hits it right at the point C, and you know, doesn't necessarily like cut through it or anything. That's what the tangent line is. So hopefully what we see geometrically, we should get that the slope of the tangent line is the limit as x approaches c, f of x minus f of c divided by x minus c, but that's just exactly the derivative, right? Maybe let me say slope of the tangent at c, just so that we see the relationship between the slope of the tangent line, but it's the tangent line at c, right? If you choose different points, you're going to get different slopes of tangents, right? And I don't think I'm going to be able to draw this. I guess I could. I could try. All right, the tangent line is something like it's not a great drawing. Also, it's starting to get a little bit busy, but the idea is, you know, hopefully you can say, oh, that's not even, I don't even think that is a terrible tangent line. That doesn't look tangent at all. Can I get rid of it? Yes. Okay, let's try that again. All right, that's a little bit better, right? That looks more tangent-y. Again, though, graph's starting to get busy. And if you're red-green colorblind, you don't have a chance for this graph. Okay, so does that make sense? And really beneficially too. So does everyone know the point slope formula? So you can get the equation of the tangent line. And I'm going to write it down here, but just out of curiosity. Okay, so y equals mx plus b. That is the slope intercept formula, right? Yeah, so the point slope formula, the idea is that every line is uniquely determined by the slope of the line, right? And also a point through which it passes. Now, the y equals mx, Kevin, exactly, perfect. The y equals mx plus b formula says that is basically the point slope formula if you know the y-intercept, right? You're saying, if I know that the function passes through the y-intercept, then I can use that in order to figure out the slope, the equation of the line. But the point slope formula is slightly more general in that it says if you just know any point through which the function passes, then you can get the equation for the line, right? So what is the point slope formula? So if the line with slope m passes through the point, I'm going to use, I think, just slightly different notation. Yeah, exactly. Yep, that is the slope. So in that case, Yuanji, what you're doing is you're actually saying every line is uniquely determined by 2 points through which it passes, and then you can use that to get the slope and then plug that into the point slope formula to actually get the equation, right? But in this one, I'm kind of assuming like we don't need a second set of points if we already know the slope, right? And which we're going to have through the derivative. So if the line with slope m passes through x naught, y naught, its equation is y minus y naught is equal to m times x minus x naught. Okay? And you can see that if the point that you use, the point through which you say the function passes, or the line passes, if that is the y-intercept, then in that case, x naught is 0 and y naught is your b, and you put the y naught on the other side, and that is precisely the y equals mx plus b formula, right? So let me show you how we use this, and I'll show you how you can just solve it to put it into y equals mx plus b. So we could say something like, find the slope of the tangent line through this, the same function that we're going to use for every example. Right? So I can say find the slope, or not the slope, the equation. Let's find the equation. Okay, so I changed that from slope to equation because we already know what the slope is. So say find the equation of the tangent line through this curve at the point x equals 2. Okay, well, we already know that the slope is given by the value of the derivative at 2. And we've already computed that, right? That was actually the very first thing we computed. It's -1/4. So the other thing that we need is a point through which it passes. Now, what you could do is you could plug this into y equals mx plus b and then plug in the points that you know, but that actually is more work than you need. So we know that it passes through the x coordinate 2, and we just need to figure out what the y coordinate is, right? So also f of 2 is equal to 1/4. So the line passes through 2, 1/4. Thus, we get y minus 1/4 is negative 1/4 x minus 2 is the equation of the tangent line. That. Okay. And if you wanted to put this into y equals mx plus b formula, that's fine. All you would do is, solve this for y. So you get negative 1/4 x plus a half plus a quarter. So that's negative 1/4 x plus 3/4. Right? So if you wanted to, there's your y equals mx plus b form. But generally using the point slope formula, it's easier to use the point slope formula to get the equation of the line and then figure out what y equals mx plus b than to go straight to y equals mx plus b, because again, you often have to do a little bit more solving, right? You have to figure out what the intercept is and then plug it back in. It's not that much more work. But the point slope formula is generally, I think, much easier, right? Especially since you already kind of know a point that it passes through. Using the y-intercept is often inconvenient, right? You already know it's passing through the point at which you're taking the derivative. Use that point, right? That's a better point to use. And if you've never seen the proof that this formula is the correct formula, I think the easiest proof actually uses, you can just do it, right? You could basically use the y equals mx plus b formula and then solve it knowing that it passes through the point x naught, y naught. There's a slightly more slick proof if you're willing to use a little bit of linear algebra and, some notion of orthogonality and such, but I'm going to leave that for you. That's sort of like pre-calculus stuff, so I'm not going to worry too much about it. Okay, any questions? We are flying. Okay. So there's another definition of the derivative. So, or in the sense that it's not another definition, it's just a different way of writing the limit. So I call this a different parameterization. I think I even call that in the book. And in fact, I actually like this one more. So let me kind of draw the picture again, the geometric picture. And again, there's kind of like an analytical way of understanding this, but I think that the picture makes this really, really easy to understand. I should have just copied and pasted this from above, but whatever. Okay. And so here's hopefully a reasonable facsimile of the picture that I drew above. And the idea here is that instead of parameterizing this as x and looking at what happens as x approaches c, what we can do instead is parameterize this by thinking about how far away x is from c, right? So what do I mean by that? What I'm going to say is that this distance here is h. H is usually what we use for that. That's not crazy. So then in that case, x becomes c plus h, right? So I'm thinking now here as h is the distance, or is let's maybe say the width of the interval. Okay. And so in that case, then if you compute what, this line is, this is called the secant line. I guess I should have mentioned that earlier, but we're rarely going to use it, so who cares? So if I compute the slope of the secant line using h now instead of x, well, again, this length here is just h. All right, that's nothing crazy. This is still, the bottom point here is still f of c. The top point is f of x, but we're going to rewrite that now as f of c plus h minus f of c, right? So we can basically, we can also write f prime of c. Okay, I'm going to write out the original definition first. It's the limit as of f of x over f of c minus f of c over x minus c. Or, and I actually do prefer this other way, but you do you. So it's the limit as h goes to 0, because remember, h is the width of the interval now, right? And we said we want to take approximations as the width of the interval becomes 0. So taking a limit as h approaches 0 of f of c plus h minus f of c divided by h, like so. Okay, and you can check that this change of variables actually works. I gave you the theorem that you need for change of variables, right? The way that you would actually do this is you'd say, maybe this is as an aside. So for the change of variables, what you do is you define capital F of x as f of x minus f of c all over x minus c. You define g of x to be equal to, what do I want here? Or just rather, yeah, I guess g of h to be c plus h. Well, let's call it x. Right. Then we know, let me just double check my notes here. So we know that, yeah, so we know that the limit as x approaches 0 of g of x is equal to c. And we know that the limit as x approaches c of capital F of x equals f prime of c. So by change of variables, x approaches 0, f of g of x is equal to f prime of c. And if you compute what capital F of g of x is, this is precisely the limit as x approaches 0, f of x plus h minus f of, or sorry, this should be f of, what did I just do here? Yeah, that's fine. So this should be c plus h minus f of c divided by h, right? What am I doing? This should be c plus x. There we go. Right, so that if you actually wanted to prove this, you're like geometrically, hopefully you're like, oh yeah, this picture is clear. Those are definitely the same limit. But if you actually wanted to prove it using like change of variables, that theorem that we talked about from like way back in the day of how you would actually, remember, and I did something like the 6th root of x as an example of how we could change the variables and able to make, in order to turn it into something we could attack more reasonably. If you actually wanted to prove that these two limits were equal, then this is the change of variables that you would use in order to make that true. Okay, so you might need to go back and reference that theorem in order to see it, but yeah, it's true. And then just to like confirm that we do get the same answer, maybe let me just redo an example above, but using this new definition. So let's say compute f prime if f is our usual function using this new definition. Okay, so I'm going to fly through this and then we'll probably be at a good point for our break. All right, so again, we're just going to compute f prime c for an arbitrary c. That this time, we're going to say that's the limit as h approaches 0, limit of f of c plus h minus f of c, all divided by h. Just to hammer that home, plug everything in. What is this going to become? C plus h squared minus 1 over c squared divided by h. And now just some algebra. So what are we going to get? We're going to get c squared minus, I'm actually going to move the c and h around and write this as h plus c squared. Obviously, that doesn't matter. Divided by h, c squared, c plus h squared. If we expand that out, what are we going to get? So we're going to get negative, 2ch plus h, or minus h squared, over h, c squared, c plus h squared. The h's cancel out. So what are we going to get? So we get negative 2c minus h divided by c squared, c plus h squared. Plug in h equals 0. I don't need to do the limit anymore. I'm continuous. Negative 2c over c to the 4, negative 2 over c cubed, right? So you get the same answer. Okay, right? So it really just, you notice that we use completely different kind of techniques here depending on how we approach this. In the original definition, we had to factor a difference of squares. That was kind of the key trick in order to get our cancellation. Here we didn't have to do any factoring. We just had to expand out this c plus h squared, or c plus h all squared term, and then do simplifications. And especially when you're dealing with rational functions, that is often the difference. One is factoring and one is just expanding out a polynomial, with factoring being the original definition and expanding out a polynomial being this definition, right? Can we show limits this way on an assignment and test, or do we have to use epsilon delta? I mean, you should use, it depends on what the question is asking you to do, right? Like this is totally fine as far as I'm concerned, but yeah, I mean, like once, I'm really heavily leveraging the fact that we know that these functions are continuous, right? Like everything up until let's say here is just algebraic manipulation, and that's totally fine, right? We can algebraically manipulate a limit as much as we want and not have to worry anything. At this point, I would normally have to use an epsilon delta, right? To do this last equal sign, I would have to use an epsilon delta. But we know that this function is continuous, right? It's continuous as a function of h because the quotient of two continuous functions is continuous as long as the denominator is not 0 at the point where you're trying to evaluate the limit. Since the denominator here is not 0, the function is continuous, and so I can just plug h in, right? I'm really, really heavily leveraging continuity in order to be able to do this. You are absolutely free to do that as well, unless the question specifically says, you do this using epsilon delta, do this using without using continuity, something along those lines. But yeah, absolutely, you can use anything that we've talked about in class. And we have talked about the fact that rational functions are continuous. So you can use that for sure. Does that make sense? There are times where actually when we're doing differentiation though, and we're evaluating these limits, we will have to go back to an epsilon delta. It's rare, but it will happen. But as a general rule, again, if your function is differentiable, this should be a removable discontinuity. So once you do enough cancellation, the thing that you get out should end up being continuous at the point, at your limiting point. And then you can just plug your number in, right? So that is usually what will happen. So it'll be very rare that you actually need to use epsilon delta for your differentiation stuff. Okay. Yeah. All right. So that's gonna take care of it for now. I think that now is a good time for us to take a little break. Let's do 10 minutes. So it's 10:02. Let's say 10:03 by my watch. We'll come back at 10:13. And we'll carry on. We'll see how much of this stuff we can get out of the way before we get into, this stuff right now is just kind of like preliminary stuff. Eventually, we're going to start doing proofs again, which is what I know everybody wants. So we'll get back to there very, very soon, hopefully even by the end of this class. Okay, so I'll see you all in 10 minutes. Take that time. And again, if you have any questions, throw them in the chat. Happy to answer them when I come back. place to get it. And like I said, we're not going to worry too much about it. So if you're kind of upset that I'm using the same function over and over and over again, that's the place to check those things out. Very easy to Google or look up my notes or countless other things. Okay. But again, if you want like me to throw some stuff at you, I'm happy to do that. But it isn't too hard to kind of do this stuff on your own as well. There's lots of practice. That's a real benefit of this course. Yeah, exactly. Thank you, Yvonne. So in my homepage, I have like all of my course notes that I've written for free. And you can find like, even if 135, 136 isn't up there, use 132, 134. And because it's basically 135, 136. And there's tons of examples in there and stuff. If you want some 137 examples, right? So slightly lower level, but still kind of proofy. My 137 notes are on that site as well. So lots and lots of resources there for you as well. Paul's online notes, I think, are great. That's typically anytime you look up, if you Google anything about calculus, you'll find Paul's online notes, and that course or that website's pretty solid. So yeah, lots of opportunity there. We're just going to dive into notation because Leibniz notation is used a fair amount. So for Leibniz notation, what we're going to do is we're going to assume that we have some sort of dependent-independent variable relationship, right? So suppose f is differentiable. And I always hate this because I feel like high schools do a really terrible job of explaining this. And y is equal to f of x, right? And the thing that drives me insane about high schools is that they conflate the difference between a function and writing y equals f of x. Do you know what I mean? So a function is just, it's a machine, right? For a function, you give it an input and it produces an output, right? You say, what is f of 2? And the answer is a quarter, right? Like we're using this function at the top here. So this is just a function. There's no y's, mentioned anywhere. It is a machine. You give me a number, it outputs a number. When I write this thing, when I write y equals f of x, this is a fundamentally different thing, right? This is saying that there are two variables now, y and x, and they have a functional relationship with each other, right? There is a function which describes how to determine y if you're given x, but the function here is a tool. It is not, this is not a function. This is a relationship between two variables that is described by a function. And there are lots of relationships, excuse me, there are lots of relationships between two functions that we can give that are not described by a function, right? Here is an equation, x squared plus y squared equals 1. It describes a relationship between two variables, but that relationship is not functional, right? There is no function which describes how x is related to y and vice versa, because we know if you graph the circle, it fails the vertical line test, right? So these are fundamentally different things. So, but what we are going to do is let's suppose that we're in this nice situation where we're told that y and x are related to each other, and they're related to each other through a differentiable function. Then we have this weird little thing called Leibniz notation. So we denote, in this case, so we denote dy dx evaluated at x equals c. So this is f prime of c. Okay, so if we write dy dx, long vertical line, subscript x equals c, what a nightmare of notation. That's the same thing as saying I'm computing the derivative of f prime of, I'm computing the derivative of f at c, right? This is the instantaneous rate of change of y with respect to x at the point c. Instantaneous rate of change of y with respect to x at c, right? What a mouthful that is. And if we just wanted to note the derivative function, we say dy dx, well, that thing is represented by f prime of x like that, okay? And what this gives rise to is a beautiful bit of notation of the derivative operator, which I'm going to use a ton, right? So we really need to know what it is. So this leads to the derivative operator, just denoted d over dx. This thing says take the derivative of whatever follows. Take the derivative of whatever is to the right. Let's be specific. If whatever is to the right of it. Right? So for example, I could say d dx, f of x is f prime of x. I could say something like d dx of y is dy dx. I could say something like d dx of 1 over x squared is -2 over x squared, all sorts of things like this, right? And so what we recognize this thing is as an operator, it says we're going to perform the act of taking the derivative and whatever comes to the right of me. And same sort of thing, if I wanted to evaluate it at a particular point, I could use this operator. So I might write something like this, and we've computed that. That's -1/4 like that. Okay? So that is the derivative operator, and Leibniz notation is generally this dy dx thing. Okay? And the motivation for why that notation is the notation that we use and comes up, it very much comes from physics. The idea is that the average change, let me actually write this in words instead of just being sloppy. So the motivation for this, so I'm going to say really comes from physics, right? Because there want to be negative, oh yeah, you're right, -2 over x cubed, thank you. So it comes from physics where you use delta to indicate the change of something. I think for any of you who have taken probably high school physics, you've seen this, or university physics, the physicists love to use delta, right, to indicate a change in something. So the motivation for this, motivation comes from physics, where delta indicates, let me make that clearer, delta indicates a change, in which case we have the average rate of change is given by delta y divided by delta x, right? Because that's y. How do I write this? This is like, right? So delta x is how much the x value has changed. And in our case, when we said the average change over an interval AB, what is the width of that interval? Well, that's how much the x value changed. And then delta y is how much did the y value change? But remember, y is equal to f of x. So the amount that y changed is precisely the difference in the f of x's. And then the physicists do the absolutely blasphemous thing where they say, therefore, dy dx is the limit as, let's say, delta x goes to 0 of delta y divided by delta x. Okay? And so the deltas magically become d's when you take this limit. So that is how the physicists do it. That is the motivation for this. You'll notice that delta y over delta x is a fraction. Of course, dy dx is not a fraction, right? Oh no, I haven't begun insulting the physicists. And anyway, so it's going to happen a lot. But more importantly, I say this as somebody who is more or less a physicist himself, right? So remember, I did a lot of physics so just as my caveat. So when no, it absolutely is not a fraction. So just as the caveat, because I'm going to really nail on physicists a lot in this course. Again, I did a specialist in physics, right? So I do have a specialist thing in physics. I actually basically have a degree in physics. And then my master's was actually in theoretical physics, right? So I say this, and I think I'm uniquely qualified to say how bad physicists are at math. But anyway, yeah, so dy dx is not a fraction, okay? Despite what Rui might say, this is not a fraction. And if any of you ever use it as a fraction, I will punish you very much. That being said, if you ever go take a physics course, they will use this like a fraction like crazy. They'll be multiplying by dy's. Yeah, and this is what I'm saying. They're not allowed to do this, right? So they'll be multiplying by dx's, dividing by dx's, all sorts of crazy things like that. And it absolutely isn't a fraction. Here's how it works for physicists. So physicists, they need to like use the math. The math has existed for a long time. So they go up to a mathematician and they say, hey, how, I need math to help me do this. The mathematician tries to explain it to the physicist, but the physicist is just too impatient. They don't care. They're like, listen, man, I don't care about all your rigor. Just tell me how to use this thing. So the mathematician then gets, visually frustrated and is very like, no, man, you can't, you have to understand where this is coming from. And the physicist says, no, it doesn't matter. Just tell me how to use it. So then the physicists say, okay, to hell with the mathematicians. I got a little bit of the insight from the mathematician of what I want to be true. They reinvent the mathematics with their own blasphemous, like meta justifications. And in fact, it's so shady what the physicists do is that often physics students will be like, well, why are you allowed to do that? And the response from the physics professors will be, don't worry about it. We've been doing it for a long time and it seems to agree experimentally. So this is how physicists justify it. And then so yes, because we can, and because it does agree experimentally, right? Like here's the crazy thing, and this is true of a lot of like really new physics that we don't have yet the math to justify, is they were doing things they are absolutely not allowed to do, right? Like they would take a math concept, they'd be like, oh, I wonder if I do this, if I take this math tool and do this with it. And the mathematicians are like, whoa, man, you can't do that. And the physicists did it anyway, and then checked experimentally, and it worked, right? Like it worked to an insane amount of precision. And then the mathematicians have to be like, oh, well, I guess they were allowed to do that. Now let's see if we can justify why they can do it. So there's some sense in which physicists can actually inspire mathematics like that, because they find that in real life, the mathematics does work, and then the mathematicians have to figure that out. So in some cases, physicists can actually help. But a lot of the time, again, the physicists just get frustrated, make up their own nonsense BS, and then it's chaos there afterwards. So trying to reconcile physics and math is actually a really hard thing to do, because the physicists do it in a completely different way, right? Yeah, you absolutely cannot, even when you're doing a differential equation, that's not what you're allowed to do. It's just that this is a nice little, like when you're doing a separable differential equation, there's like this nice, separating the dy and the dx is what do I want to say? It's a trick that you're not allowed to do. There's a rigorous justification behind why you can do that trick. So, and that is frankly how everyone learns it, right? When you're learning separable differential equations, that is how everyone does it. But what you're doing there is not legal, right? That's just kind of a shorthand to hide the rigorous thing that's actually happening. So in theory, yeah, you did learn it the wrong way, but you also learned it the right way in the sense that that's how everyone learns it, if that makes sense, right? But yeah, that is not a fraction. Don't treat it like a fraction. What's worse is that even though I say it's not a fraction, we will see countless times in this course that it does behave like one, right? That it cancels in exactly the way it should cancel. There will be just dx's by themselves at some point, and I'll be like, ignore those. Like, they're there, we put them there, but you don't know what they mean. They're too complicated. So these sorts of things unfortunately do happen, but I do have to say they are not fractions. Do not treat them as fractions. Okay, otherwise there will be hell to pay. Okay, so higher order derivatives. The idea now is that you've got a function, you differentiate it, you get f prime. F prime is also a function, maybe you can differentiate it, right? So after differentiating, a function, we get a new function called the derivative, right? And the name if you didn't know, why do we call it derivative? It's because it's derivative of f, right? Like if you think about what the English word derivative means, it means derived from, right? As in it came from something else, right? And f prime comes from f, right? We use the information about f in order to figure out the information about f prime. Therefore, we would say that f prime is derivative of f. And over time, we just kind of started to call it the derivative of f, if that makes sense. Right? Like if you think about someone talking about, oh, yes, you know, his artistic style is so derivative, as in like it's very much like inspired or came from somebody else's art style, right? Like it's not original. That's what we're saying. F prime here is not original. It's very much inspired by f. Its information and data comes from the original function f, right? So after differentiating, we get a function called the derivative f prime. This is also a function. Hopefully we can differentiate it. So if we can differentiate f prime, we get, okay, so strictly speaking, this would be f prime prime, but that's a little bit kind of nasty to write down. So we often will write f double prime, and this will be the second derivative of f, right? Right, and same sort of thing. You might take f double prime prime, that would give you f triple prime, that would be the third derivative. But you can imagine like continuing in this exactly. And Stephen, I would suggest a better notation might be this. If you were really going to do it, like that's how I would, just so you can count, because otherwise, like I have no idea how many apostrophes are in your f, at least this way, which is, again, just totally not an okay way of doing it. But at least it's very easy for us to tell that this would be the 10th derivative, right? But so no, in practice, we don't do that, right? This is bad. Don't do that. Basically, after the third derivative, you start indicating it like this. So you put that into brackets, and this becomes the nth derivative. Okay. The higher derivative at some point, f triple prime will be equal to 0. It depends on what you mean by that. I mean, that doesn't have to be true, right? I mean, certainly I can find functions where the third derivative is not 0. Ever, right? So yeah, it depends what you mean, Adam, by like that sort of by that statement. But yeah, so we use this bracket. Oh, I guess you know what? Oh, I should have. I'll mention it later. No, I should mention it now. Okay. The physicists. So back up in notation. This is a little aside. This is some of the worst notation in the world. Never use this notation, but I'm going to introduce it just so you know. So again, if we have y equals f of x, some physicists will use the dot notation to mean f prime of x. And then y double dot will be f double prime of x. And then y triple dot will be f triple prime of x, like that. Okay. So mathematicians use this. This is called Fluxin notation. This is actually Newton's original notation. So this is how Newton indicated derivatives. This is garbage. Don't use this. Again, the physicists sometimes do use it. You tend to see it, especially in mechanics and Lagrangian mechanics. So if you're doing physics, this is used a lot in Lagrangian mechanics, and there it's not too bad. But basically, it doesn't generalize well beyond like 2 or 3 derivatives. Okay. Yeah, it definitely shows up. Like I said, go take a look at Lagrangian mechanics. In fact, pull up the Euler-Lagrange equation. So look up the Euler-Lagrange equation. Why is my pen not working? So if you just put this into Wiki, I'm pretty sure you'll see this notation come up, right? And the Euler-Lagrange equation is, I mean, it's important mathematically as well. Exactly, yeah, the Lagrangian. It shows it's very important mathematically as well, but like the place where it's so crazy useful is in variational calculus and especially classical mechanics, right? So the Euler-Lagrange equation, you will see that notation pop up because you're taking the derivative with respect to like the second derivative. It is a weird thing. Like variational calculus is super cool. And again, it's really one of my favorite fields of mathematics. it is a big part of what I did my master's in, but it doesn't change the fact that it's a weird field, right? Okay, so let's do an example, and let's find the third derivative of our classical function. So find the third derivative of our function, 0 to infinity to r, x maps to 1 over x squared. Okay, and we already know what the first derivative is. So we're just going to differentiate that. So we're going to do f double prime at c. That's going to be the limit as, what do I want to use here? Let's do h goes to 0 of f prime c plus h, f prime of c divided by h. H goes to 0. Okay, so this is what? -2 over c plus h squared cubed. Am I going to regret this? I might. Plus 2 all over c cubed divided by h. And then limit as h goes to 0. So I'm going to pull out this -2. Well, let's pull it, -2 over h out. So I'm going to get c cubed minus c plus h cubed all over c cubed c plus h cubed. Hopefully I did that right, but if you see math errors, let me know. Chat's not exploding yet. -2 over h. Okay, so what am I going to get here? So I'm going to get -c squared h minus ch squared minus h cubed. Right, then I can cancel some h's. H goes to 0. Maybe let me put the minus sign back in too. So that'll make life a little bit easier. So I'll get 2c squared plus 2ch plus 2h cubed divided by c cubed, c plus h cubed. All right, this thing's continuous. I plug h equals 0 into it. I'm going to get 2c squared all over c to the 6. Why do I feel like I'm missing? Oh my God, I've missed all the 3's. There we go. Six over c to the 4. Because I forgot my binomial expansion, right? Can we use the formula for derivatives that we haven't proved them yet? If you prove them, you can. Right? Remember the other in office hours, if you were there, and I think you were, when we were talking about sequences, and Victor wanted to use sequences, and I said, yes, you can use anything you want about sequences, but you have to prove those things first. Yeah, so same thing. Like if you want to use L'Hopital's rule to do stuff, yeah, you can do it, but you have to prove L'Hopital's rule first. Okay, so there you go. There's 6 over c to the 4. So this is the second derivative, right? Or maybe let me add in another line here, right? So thus, again, it's differentiable everywhere. So it still maps from 0 infinity to r. And it is 6 over x to the 4 is the second derivative. Okay, and again, these sorts of things are really important, and they show up a ton in physics. So again, if we use our kind of, if the function f is the distance that you've traveled, f prime is the speed. What's f double prime? Does anyone know? What is the second derivative? Okay, we just sure. What is a? What does a mean? Right, it's acceleration, right? So a is the acceleration. What is the third derivative called? Does anyone know? Jerk. Yeah, very nice. Yeah, so the third derivative is the jerk, right? So it's how quickly your acceleration is changing. Yeah, the change of a. That's, yeah, another nice political answer. But yeah. Yeah, and I think actually, Yvonne, those are like the fourth, fifth, and sixth derivatives, right? I think those actually are the like tongue-in-cheek names of those things. I somehow recall that being true. But at that point, nobody uses them, right? like when you're modeling differential equations, it's rare that you even use the third derivative. But second derivative, first and second derivative show up a ton, right? Just a ton. Okay, and so now let's do some like quote unquote obvious things. Let's get back to proofiness. Okay, so proposition, I'm not proving this one. This one's for you. If f maps I to R is a constant function, then f is differentiable and f prime of x is equal to 0 for all x and I. Okay, so that's on you. You can prove this. This proof is very straightforward, right? Just write out what the definition is. You'll be like, oh yeah, that falls apart almost immediately, okay? So the derivative of the constant function, so the constant functions are everywhere differentiable and their derivatives are 0. Now, it turns out the converse of this theorem is true as well. If I give you a function whose derivative is everywhere 0, then it is the constant function. However, we don't have the tools yet to prove that, okay? So you don't know that that's true, but the opposite direction is true as well, okay? The only functions whose derivative is everywhere 0 are precisely the constant functions. So that's proposition number 1. Proposition number 2 is a nice linear algebra fact for anyone taking linear algebra. So let's suppose that f and g are differentiable at C, and alpha is a real number. So 1, f plus g is differentiable at C. And yeah, the exactly what you want to be true is true. Right? The derivative of the sum is the sum of the derivatives. And to same thing for alpha times a function, right? So we're saying the derivative here is linear. Was anyone by chance taking either 224 or 240 right now? Well, I guess you can't be taking 240 right now unless you're taking it downtown. Yeah, you are? Okay. Okay, sweet. So, I mean, Howard, at least you, exactly, the derivative operator is a linear operator. Yeah. Okay, so Tianren, you, so for those of you who have seen some linear algebra, at least, even 223 possibly, you know about linear transformations, right? Maps between vector spaces. And if you've only taken 223, you might not know what the word vector space quite means yet, but you've probably seen linear transformations. So you'll notice that the derivative map is precisely a linear transformation, right? Assuming that the functions are vectors, you have d dx of f plus g is d dx. And I'm kind of putting brackets here, even though normally we wouldn't, just to really make that clear. And d dx alpha f is alpha d dx of f, right? So, I mean, first of all, even if you're not taking linear algebra, this can be a nice way of remembering this. If you are taking linear algebra, or when you do eventually take linear algebra, you'll be able to see this and you'll be like, oh, hey, cool. Yeah, I mean, the derivative is very, very much linear. Okay, so you'll learn about what a linear transformation is, and you'll be able to be like, oh yeah, Tyler was talking about linear transformations. This is clearly a linear transformation. And in fact, the collection of differentiable functions, actually, you need to take C infinity functions, but if you take the collection of C infinity functions, well, okay, differentiable functions are a vector space, but then the derivative is not a linear operator because the derivative of a function need not be differentiable, yada, yada, yada. Whatever, let's not worry about that. Okay, go ask Asan when you get to 240 what I'm talking about. Okay, so I'm going to prove number 1, 224 this term. Nice, right? So then in that case, you actually have seen linear transformations, and hopefully the fact that C infinity functions are a vector space. Okay, I'm going to prove 1 for you. 2 is way easier, so I'm going to let you prove 2. So for the proof of 1, so we want to show that f plus g is differentiable at c. We have to prove 2 things. F plus g is differentiable and the value of the derivative. But again, if I prove that f plus g prime of c is f prime plus g prime, then that means f plus g prime exists, so it's differentiable, right? So we kind of like knock both of those out at the same time. And the proof here is, again, just kind of compute it, right? So we're going to get f plus g prime of c. That's going to be the limit as x approaches c, f plus g, I guess I'm using brackets, of x minus f plus g of c divided by x minus c. And you can split these up. It works out. I'm going to have to go to a new line here. I'm not going to have enough space. If you have space, though, you don't have to erase that. But you can just split these up as it works out exactly to split up like this, right? So this proof isn't particularly hard either, right? But you can just split it up like that. Now, at this point, you want to use the limit laws, right? You want to say the limit of the sum is the sum of the limits. But in order to do that, you need to know that both limits exist in the first place. But luckily, we do have that, right? We were told that f and g are both differentiable. Therefore, their limits exist. And because their limits exist, I can use the limit laws. So I can split this up. All right, so plus the limit as x approaches c, g of x minus g of c, right? So this is because since f and g are differentiable at c, right? If you don't know they exist, you can't split them up, but I can split them up because I know they exist, and voila, there we go. Right, and I'm done. And the proof of 2 is exactly the same, only way easier, right? So when you do the proof of 2, when you have this like alpha, the alpha just comes right out of the limit. Again, by the limit laws, you know the limit exists, so you can just factor that alpha out and boom, you're done, right? It's much faster. It's about half the amount of work. Okay, so the derivative is linear. This is nice. So now if you're asked to compute the derivative of the sum of 2 functions, you don't have to go through your limit definition again. You can just be like, oh, I know the limit, or I know the derivative of each of these functions separately, and now I can combine them into a thing. I think, let's see, it's 10:48. Do I have time to do the product rule? Probably. Theorem, so the function f from R to R, x mapping xn is differentiable for any n in the naturals and f prime of x is nx to the n minus 1. Yeah, that's true. Then you can use it. Okay, so this is called the power rule. Maybe just let me write that down here. The power rule. Note right now, this only tells you for natural number exponents, right? It doesn't tell you that this is true for negative exponents. It doesn't tell you it's true for rational exponents. And especially it doesn't tell you true for real exponents, right? Now, it will be true for all real numbers, but we don't know that yet. Okay, so right now, the proof that we're going to do is only going to be true for the naturals, and then we have to slowly start building it up and expand it to other things as well. Okay, so the proof, you can use either definition of the derivative. They're pretty similar. Again, it's a difference of whether you want to expand, in which case you have to use the binomial theorem, or whether or not you want to factor. Now, in this case, I'd actually prefer to factor. So let's compute f prime. So I'm going to do, let's say, f prime of c. So that's the limit as x approaches c, f of x minus f of c divided by x minus c. And if I just plug all that in, x to the n minus c to the n all over x minus c. Now, clearly, x minus c is going to be a factor of the numerator, because if I were to plug c into that, I would get 0, right? So I know that x minus c factors. To see how it factors, we need to remember, so maybe let me just kind of put this on the side here. So recall that x to the n, here's how you factor a difference of nth powers. So this is going to, and then what, x to the n minus 1 plus x to the n minus 2c plus dot 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 plus x c to the n minus 2 plus c to the n minus 1. Okay, so that's how you factor a difference of nth powers. So you can see that if I factor, or if I divide the x minus c out, I'm just going to be left with this big old sum here, right? So I'm going to get the limit. It's definitely easier if you just use sigma notation. So x c to the n minus 2, c to the n minus 1. And there are exactly n of these terms, right? So if you count this, how many of these things are there? There are n of them. Okay, and now this thing is continuous. So you can just plug x equals c into it. So what do you get? You get c to the n minus 1 plus c to the n minus 1 plus, they all just end up being c to the n minus 1s. And there are exactly n of them. Oh, I shouldn't have the limit here because I've already plugged the number in. So that gives me n c to the n minus 1, right? So this exists. So f is differentiable. And f prime of x is nx to the n minus 1, like that. Okay. Oh man, yeah, I proved that in like 3 minutes. Okay, but again, so this proof relies on the fact that I'm doing it for a natural number n. I guess, like, technically speaking, if n is equal to 1, you should do a separate case, right? Because it's like you don't get this. Well, I guess maybe you do. Let's just double check. If n is equal to 1, yeah, I guess you do get this factorization just because the sum is stupid, right? It's just, it gives you 1. So I guess this is still true there as well. But yeah, in order to be able to factor the difference of the nth powers have to be natural numbers, right? If this is like x to the power of -3 minus c to the power of -3, this expansion doesn't necessarily work. So here it is critical that these are positive whole numbers when I do this expansion. So I know that it's true for all the natural numbers, and it's certainly true when n is equal to 0 as well. So if you want to include 0 as a natural number, you know, who cares? And we're good, right? So now we have that. Yeah, sure, right? So yeah, so now you know this for all natural numbers, regardless of whether or not you include 0 as a natural number or not, and you have the power rule, okay? So this is great because combined with linearity and the power rule, you can now differentiate any polynomial, right? So we can now, maybe just let this be the last thing I say, we can differentiate any polynomial, right? Because the derivative of the sum from k equals 0 to n, ak x to the k minus 1, becomes, oh, sorry, why would I do k minus 1? Is k a k x to the k minus 1, like that, right? Or maybe as a concrete example, just making something up, x to the 4 plus 2x squared minus 7 is 4x cubed. I did not make them both 4 on purpose. It is something like that, right? And so there we have it, right? So we can now, every single polynomial is accessible to us with both linearity And the power rule, every single thing that I could want about polynomials ends up being very quickly and easily differentiated. Okay. Okay. So that was 2 hours. And, you know, I always like to think people are always like, oh man, university moves so much faster than high school. And I try and think about like when I was doing high school calculus, how long it took us to cover that much material. And I think it was a couple of weeks that we just did in 2 hours. Right? What do you figure? How long would you have spent on that in high school calc? Probably not 2 hours, right? So now you can go back to your high school friends or your high school teacher and you're like, yeah, you know, all that stuff that you spent half the semester doing. Yeah, we did that. And that was like one lecture, right? And now we get to go and do other things. So yeah, basically on Thursday, I'm going to try and knock out product and quotient rule. And if we finish early, fine, whatever. And we can do office hours for the rest of the class before the actual test starts. So that's the goal. I want to knock those two out. And then next week we'll do chain rule and the inverse function theorem. So chain rule obviously being, you know, super important, probably the most important of the derivative rules. And then the inverse function theorem, which is probably new to most of you. But maybe not, I don't know, we'll see. I have no idea what they teach in high school anymore. But yeah, so we'll do the inverse function theorem next week. Okay, so that's our plan. That's going to take care of it for today. Again, if you haven't seen calculus before, just give this stuff a review and let me know if you're having any troubles with it. It's fairly formulaic. Try a couple of examples and see where you are. And then, you know, post on Piazza, post on Discord or whatever. And I'm happy to help, right? Because I know I went through this stuff very, very quickly. All right, everyone. So yeah. Is it also open book? Yeah, it's the exact same as the last term test. Same format. None of the rules have changed. Everything is the same. Yeah. Yeah, also 3 questions. Though, I mean, you don't know how many parts there are. Okay, everyone? All right. What is the recommended time we spend on it? I mean, it's designed that you can write it in 2 hours, but no, it's 3 questions total. Some questions have multiple parts. It's supposed to be writable in 2 hours, but you can spend as long as you want on it, as long as you are comfortable doing that. Same thing with my 257 exam. I asked my students in that class, I gave them 24 hours as well. And some of them spent 8 hours on it. Like, it was not, they didn't have to do that, but they wanted to. Like, they, you know, had a question in front of them. They knew they had the time to do it. They wanted to spend 8 hours on it. Who am I to say, don't do that, right? You spend as much time as you feel comfortable that you need to spend on it. But I think like after 2 or 3 hours, you'll probably know whether or not you can solve the rest of the questions, right? Like, if you get stuck, you're just like, oh man, I don't know what to do anymore. And probably thinking about this for another 5 hours isn't going to make a difference, right? Thank you. Okay, everyone, I'm going to kill the meeting now unless there are any last minute questions. Thank you too, thank you. Okay, everyone. People are dropping like flies, but that was the point. All right, everyone. Okay, I'm going to close the meeting now. Thank you. Have a good day, and I will see you first thing on Thursday. Ciao.